Hello and welcome to this session on harmonic and transient dynamic response analysis. The two modules are similar in many ways because they both analyze how the structure responds to loads that vary with time. In the case of harmonic, the loads vary in a regular sinusoidal manner, whereas with the transient module, the loads can vary with time in any general manner. Note that transient response analysis is sometimes also known as time history analysis. I'm going to start with harmonic, but even if you're only interested in transient, it's worth watching the harmonic first because quite a few of the operations I'll be showing are common to both modules. So harmonic analysis is used to model loads that vibrate in a harmonic or a sinusoidal motion, such as you could get with a crusher or a pump, a vibrating table, a motor, or any out of balance rotating or oscillating mass. It could also be used to model the effect of traffic on a bridge or a footfall analysis. So if I go to the help menu and just show you the section of the manual on harmonic analysis, this is an example of a rotating mass about some central point at an angular velocity of v, and the centrifugal force is, as you know, mass times acceleration. The acceleration is v squared over r. And so the centrifugal force is mv squared over r. And so if you're modelling the effect of this rotating mass, you would calculate that centrifugal force and then just put that in as a node load. So in this structure, which is like a gantry structure that's supported at both ends, we've got 4 oscillating loads, so 2 here and 2 up here. They're 2.14 kilonewtons each, and so that 2.14 is simply the mass times the maximum acceleration of the oscillating load. So in order to do a harmonic analysis, the first thing we do is set up a harmonic load case via this data sheet. Let's call it load case 100. The source case is the load case that's got the harmonic loads in it, which is this one here, so it's got the 2.14 kilonewton oscillating loads in it. The problem type allows us to choose the type of analysis we want to do. So for this particular example we're using applied loads, but if you've got a situation where the base of the structure or the support part of the structure is vibrating, you could also model it as a base displacement, base velocity, or base acceleration. So you might use some of those for an example of like a shaker table or something like that. We've got our masses in load case 90. Moving across to the factor, so it's normally 1, but if you wanted to factor up or down the effect of the harmonic loads, you could put a factor there. We need to specify the frequency of the vibrating loads, so in this case it's 0.8 Hertz, and a phase. So the phase represents where the load starts in the sine curve of a typical oscillation. So a phase of 0 means that it's the start of the oscillation, 180 degrees means it's halfway through, and 360 means that it's at the end of a typical oscillation. So we click OK. Because the harmonic analysis requires you to do a dynamic frequency analysis, or it uses the results of a dynamic frequency analysis, we need to do that first. And once it's done, you don't have to keep redoing it, but I'll just run through that now just to make sure that it's been done. Before I do, I'll just show you which masses have been defined in our mass load case 90. So going to the mass data sheet, lump mass data sheet, you can see that we've got some masses in various load cases here, and these represent the masses that contribute to the inertia of the structure. So there could be things like mass due to dead load or live load or anything else attached to the structure. You'll also notice that we've used the same value in the X, Y and Z directions. So if the vertical axis is Y, you'd probably think normally the mass is just a vertical mass, but when the structure is vibrating, the masses also have inertia in the 2 horizontal directions, so that's why we put the same value in all 3 directions. We're also including self-mass in this analysis. So to model self-mass, you just go into the self-weight data sheet, and the load case that you want the self-mass into is, in this case, number 10. We're putting a -1g vertical acceleration. Now in terms of self-mass, all we really needed to do here was just specify the mass load case and put anything into any of these three columns. So it really just treats any entries as just a signal to calculate self-mass, and the actual values don't really matter. So we'll close that. We've created a combination load case. This is number 90 that we're actually analyzing as our mass load case. That's a combination of the self-mass and then those lump masses from load case 96 and 97. So let's do the dynamic frequency analysis. One of the things you need to check with dynamic frequency is that you get a sufficient mass participation factor. So we try to get as close to 100% as we can, but because that's not generally practical, the code lets you use anything above 90%. In this particular case, we're interested in the vertical direction, but we've only got 87% mass participation, so we need to repeat the analysis and just include a few more modes. So let's bump that up to 100 and see what happens. Okay, so this time we're just over 90, so let's say we're good to go. So now I can do the harmonic analysis. And just going through this form, at the top here we've got the harmonic load case that we defined in the data sheet. In the next field we can list the modes that we want to include in the harmonic analysis, and normally you would include all the ones that have been analysed in the dynamic frequency analysis simply by leaving this field blank, so that's what I'll do in this case. Moving down, we've got the damping. So as you know, damping is caused by things like friction at the steel connections, or opening and closing of microcracks in the concrete, fireproofing, or friction between the structure and the non-structural elements such as partition walls. So you can have a damping turned off, which is not really practical, so let's not do that. Or we could have modal damping, which is a constant damping ratio for each mode, and this is the most commonly used method of damping. So for steel structures you would normally use something around 5%, or for reinforced concrete structures somewhere between 5 and 6%. We've also got rally damping, which is a little bit more sophisticated, where the damping is proportional to a combination of mass and stiffness, and this can be controlled with some parameters that you can get to via this button here. So there's information in the help file about rally damping, and there's also plenty on the internet, so I'll leave it to you to investigate that further if you want to use it. So we'll switch to modal damping and we'll use 5%. Further down you've got a choice of time or frequency sampling. So during a harmonic analysis, if we use time sampling, we're basically seeing what happens to the structure over the period of time that we specify here. So in this case, let's say we go from time 0 to 10 seconds. And we can also specify the number of steps. So if I make it 200 steps, that's 200 time intervals, or 201 snapshots of what the structure is doing throughout that 10-second period. And then click OK to run the analysis. So we get a summary of, again, the mass participation factors, and then a summary of the maximum translations, rotations, velocities, etc. That just gives you a small snapshot of how the structure has responded. So we'll click OK, and the next thing I'd probably do is run an animation just to see how the structure's reacted to those loads. So load case 100, that's our harmonic load case. The animation speed can be sped up or slowed down, and if you choose somewhere near the middle you'll get a real-time animation. You can also tick this box to get it to repeat after it's done its 10-second period, which the 10 seconds comes from what we specified in the analysis, and if you put a value in here then it will pause for a number of seconds before it repeats. So you can change the scale of the animation just by holding down the D key and rotating your mouse scroll wheel. If you ever try to get an animation and nothing happens like this, it's possibly because the scale is set too low. So in that case, just try holding down D and then rotate the mouse wheel forward until you see something happening. We can also get a graph for any of the nodes to show the motion that we're getting. So let's say I pick a node in here somewhere and right click on it and then choose Harmonic Transient Response Graph. Choose the load case that you're interested in and the diagram type. So it's actually quite important that you choose this correctly because the default is an X displacement diagram, which in this case is not what we want. So we want a displacement diagram in the Y direction for the vertical axis and time for the horizontal axis. And so you can see the displacement motion of that node over a period of 10 seconds, and from that you can tell that it deflects to a maximum of a bit more than 0.6 millimeters each cycle of the oscillation. So in this particular example so far we've got our 4 loads here that are vibrating in phase at the same frequency. So what happens if some of the loads are out of phase with respect to the others? So let's try that by just moving these 2 loads into a different load case. So I'll select them both and I'll move them into load case 41. So if you're going to give them a different phase or frequency, then you need to have them in a different load case to the other ones. Then we go back to our harmonic datasheet, and still in harmonic load case 100 we're just going to add another line of data to it. So now we've got load case 41, which is the 2 loads at the right hand end, same mass load case, and I'm just going to use a phase of 180 and keep the frequency the same as the other 2 loads. And then reanalyze. So you'll notice I didn't have to do the dynamic frequency analysis again. That's obviously saved, so you just do it once. And then we'll look at the animation again. So straight away you can see it's a completely different action now that the loads are out of phase with each other. So let's try it with out of phase by 90 degrees instead of 180. So different motion again, a bit more like a wave motion now. Similarly, if some loads are operating at a different frequency, we can do the same sort of changes to model that. So if the 2 right-hand loads are operating at, let's say, 1.2 Hertz instead of 0.8, we'll see what effect that has. So now you can see the motion is much more involved, and it changes as the loads go in and out of phase with each other, because now they're operating at different frequencies. So if I look at the motion of one of these nodes here, now you can see the curve is much more involved. It's still a repeating cycle, so the cycle starts here and then begins again here, so about every 2.5 seconds it repeats another cycle. So strictly speaking, I could have, instead of analyzing for 10 seconds, I could have just analyzed for say 3 seconds and just captured one cycle, because really after that first cycle it's just more of the same. The main reason you would do multiple cycles is just so that the animation runs for a bit longer and you get a smoother animation. The other thing you can do with a harmonic analysis is run frequency sampling. So instead of varying the time from 0 to 10 seconds, we might want to vary the frequency, let's say from 0 to 20 Hertz, and see what those different frequencies have on the structure, what effect they have on the structure. So instead of using the 0.8 Hertz and the 1.2 Hertz that we specified in the harmonic load case, it's now going to vary the frequencies over this range, and we'll let it go 500 steps. This one involves a few more calculations, so it takes a little bit longer than the time sampling. And then if we look at the diagram for a node, now you can see we get a completely different sort of graph. And this is actually a resonance curve that just shows that if the frequency was somewhere around 4.5 Hertz, that the structure would be close to resonance, so it displaces a large amount compared to other frequencies that are nearby. So we've got a peak at 4.5 Hertz. We've also got another one at about 10 Hertz, and then smaller ones further along. Generally speaking, these peaks will correspond with the natural frequencies of the structure, but the amount that the structure responds to them is unknown until you run this type of analysis. So that's a summary of how you can run the harmonic analysis and get animations and graphs showing how the nodes move. But in order to use them in a real design, we need to convert the critical steps in a typical cycle into load cases that give you deflections, forces, moments and reactions, just like you'd get from a static analysis. So I'll be showing how to do that shortly, but before I get to that, I'm going to now switch over to transient analysis and just show how it can be used to model other situations. So using the same structure, I can create transient load cases as well. So let's start with, let's call it 100, load case 101. I'm going to use the same information as I used in the harmonic analysis, and for my problem type I'm going to say it's a harmonic problem type. Same mass load case. Save that, and then this time run a transient response analysis or a time history analysis. So I'll use the same data as before, 10-second time range, 200 steps. You'll notice there's no frequency sampling with transient dynamic analysis, and that's one of the advantages that harmonic analysis has got over transient. So if we show the animation, and as you can see, it's vibrating in a similar fashion to the harmonic analysis. One thing you might notice is at the start of the analysis there's a bit of jumping and shaking going on, different to the normal oscillations. It's about to restart, so that little section there that it does. And I'll just explain that by looking at one of these nodes again. So you can see here in the second part of the curve that it's similar to the harmonic analysis, but at the start it's jumping around a little bit more and looking a bit weird. So what's happening here is that we've applied the load suddenly to the structure, and the structure reacts to that load initially slightly differently to when it's settled into its steady state oscillations. So we call this phase at the front here the transient phase, and then after that it's followed by the steady state phase. So the transient analysis gives you that transient phase, and then the steady state phase, where the harmonic analysis is only concerned with steady state. So that's just one example of a transient analysis. It can also be used to model any regular or arbitrary time-dependent load rather than just harmonic loads. You can model things like wind gusts, seismic events, vibrating machines, blast loads, pulse loads, moving traffic, etc. And they're all selectable by the problem type. So when we come in here and create the transient load case, we can choose not only harmonic but also just normal applied loads that get applied to the structure over a period of time, or for example initial displacements, which are displacements that are assumed to be present at time 0 and then are removed, causing the structure to react and then settle into a new state of equilibrium. Base accelerations can be either translational or rotational, and they can be used to model seismic events or some sort of acceleration due to the structure being moved or shaken. So I'm going to show an example of a rotational base acceleration shortly. And periodic loads, they are similar to harmonic loads in that they repeat, except that they follow any arbitrary time-dependent pattern rather than being strictly sinusoidal. So for example, a periodic load could be caused by a propeller force on a ship, or wave loading on an offshore structure, or wind forces induced by vortex shedding on tall slender structures, and things like that. So let's create a new load case. We'll call it 102, and this time I'm going to introduce some loads in load case 50. We'll use applied loads. I'll use the same mass case as before and a factor of 1. So load case 50, just so that I can explain it, are just some static loads. So these aren't vibrating loads now, they're just some static loads that in this case are 10.23 kilonewtons, and they are just going to be applied suddenly to the structure, and then we'll see how the structure responds to those loads over a period of time. So we'll run the analysis, and I'll just do it for load case 102 so that it's not wasting time with load case 101. And then have a look at the animation. Scale it back a little bit. So we'll just wait, it's nearly at the end of the 10 seconds, so let's let it repeat. So you can see the load gets applied suddenly and the structure responds, bounces up and down a little bit, and then settles into its new deformed position. So looking at the graph of a typical node again, just checking I've still got the right diagram. So the y displacement of that node starts at 0, we suddenly apply the load, so you can see it's bouncing up and down a little bit, and then it settles down to its equilibrium position of, in this case, 2.98 millimeters deflection. So that 2.98 is no different to what we would get if we just did a static analysis of this load case. And let's actually do that and just compare. So if I do a static analysis of load case 50, and I could show the deflected shape, and maybe just interrogate that same node and look at the results. So you can see we get the same value, 2.98 millimeters. Obviously the transient analysis gives you much more information, because as well as the final deflection, you also get these initial deflections, which you can see are much higher than the 2.98, so it's almost double that deflection when the load is suddenly applied. So what happens if the load is applied and then removed? Well, we can also do that in a transient analysis by specifying a factor versus time table. So if you don't have a factor versus time table, then it just assumes that the load is applied suddenly and maintained. But with a factor versus time table, we can do more than that. So let's say at time 0 we've got no load, and then 1 second in we've also got no load, but we start, well, let's say we apply the load at 1 second, hold it for, let's say, 5 seconds, so at the 6 second mark the load is still applied, and then straight after that we take the load off. So there's the graph. So nothing happening for the first second, and then the full load applied for the next 5 seconds, and then it's removed. So the button here goes red just to let you know that you've got some data in there, in case you forget. Reanalyze. So you see the effect. And if I look at that graph of that node again, so we've got the initial 1 second where nothing happens, then we apply the load, it bounces around, settles down to the 2.98 millimeters, and then we take the load off, so it bounces around again and comes back to 0. We could also apply the load gradually instead of suddenly like that, just by changing the factor versus time table. So let's say at 2 seconds we apply it, so we've done it a bit more gently now, and let's say we also take a second to remove the load, so this will make it not bounce around quite as much. So you can see it's much more gentle and there's much less dynamic effect involved. And looking at the graph again, so you can see much less oscillation, but still the same final equilibrium deflections in the deformed position and in the undeformed position, but just a different response to the loads. So before I get off the factor versus time tables, I'll just show that you can also create a curve, so it doesn't have to be just discrete points. We could go in here and create a curve, so we could put in an equation in this field here, give it a start and finish period for the curve. So I'm just going to do a sine curve, and I'll approximate it by, let's say, 100 points in the curve. And so you can do that sort of thing as well. You can make any sort of curve you want, parabolic or whatever shape you like. Similarly, if you've got this time versus factor data in a spreadsheet or some other program, you can just copy or paste that into the table directly. So now I'm going to switch over to another job and demonstrate a rotational base acceleration. So this is a stacker structure that's supported at a pivot point here on a post, and it's got wheels at these 2 points here. And so when the stacker wants to move position, these wheels run on a curved rail and rotate the whole stacker about this point here. So this is node 13, and the distance from node 13 to the wheels is almost 30 meters. So if we wanted to analyze the effect of the acceleration on the stacker as it starts moving in a skew direction, we can do that by creating a transient load case. Let's call it load case 100, and this time, instead of applied loads, I'm going to choose base acceleration rotation. And once we do that, you can see there's no source case required because it's a base acceleration. The mass case in this particular example is 41. The rotation node is 13. That's the node down here at the bottom of the post. And the rotational acceleration is quite gentle, 0.0056 radians per second squared. Now we're also going to specify a factor versus time table because when it's slewing, the stacker is accelerating, or the two wheels up the right hand end are accelerating to 10 meters per minute over a period of 10 seconds. Then it's keeping a constant velocity for another period, and then it's decelerating back to zero over another period of 10 seconds. So we need to specify that in a factor versus time table. So we start with nothing at time 0, and I'm just going to let it do nothing for the first second. Then the load or the acceleration is applied after 1 second. It's held constant for 10 seconds. Removed at that point, so now the stacker is moving at a constant velocity, and then after another 10 seconds of the constant velocity, we're going to start decelerating. So the 10 seconds of constant velocity could be larger than that in real life, but because there's no acceleration happening, we can just shorten it down to something more manageable because nothing is really happening to the structure over that time anyway. So we're decelerating for 10 seconds. And then the deceleration stops. So just going over the curve, there's nothing happening in the first second. The acceleration is applied for 10 seconds. Then it's running at constant velocity for the next 10 seconds, and then decelerating for the final 10 seconds. So let's analyze it. I'll just check the dynamic frequency analysis first. So you can see here we've only got 3 modes as the default. That's nowhere near enough, so let's try 20. 20 is usually a good place to start. And if then the mass participation factor is not up to 90%, then you'd try a few more modes. We're interested in the deflections in the Z direction because that's the slew direction. So in that Z direction we've got 98.8% mass participation, so that's plenty. And then we run the transient response analysis. I could leave the load case list blank and it would then analyze all of the transient dynamic load cases, but I'll just put in that one. So let's run it over 40 seconds because it takes that long to get through the acceleration and the deceleration phases, and 500 steps. And then just have a look at the animation. So this is an example of what I mentioned before about expecting to see something but nothing's happening, and it's probably because the displacement scale is not high enough. So I'll just hold down the D key and rotate the mouse wheel forward a little bit. It's just in the constant velocity section here at the moment, so there's not much happening. Just exaggerate the scale a bit more. And maybe just start that again just so that you can see it properly. So that's the structure accelerating, slewing to the left. Then the acceleration stops, so it's just moving at a constant velocity now for 10 seconds. And then it's decelerating for another 10 seconds. And then once the deceleration stops, then it goes back to its equilibrium position again. So just looking at the displacement of one of these nodes at the tip, so we're interested in the Z displacement here, and I'll just enlarge this. So here you can see the node is at equilibrium. Then we apply the acceleration, so it bounces around a bit and then reaches a deflection of 0.6 millimeters, not very much. The acceleration stops, so it's back to zero deflection again while it's in its constant velocity phase. And then the deceleration starts, so again it bounces around a bit more, goes back to 0.6 millimeters in the opposite direction, and then eventually goes back to zero when the deceleration stops. So as I mentioned before, in order to use the results of these types of analysis, we need to convert the steps of the critical positions to load cases that contain deflections, forces, moments and reactions. So in order to do that, we go to the Loads menu, choose the Generate Dynamic Response Step Load Cases option, and in this form we're going to create the load cases from Transient Load Case 100, and we're just going to create load cases, let's say begin at load case 201, and we just want the steps at the minimum and maximum values, so these will give us the worst case values from the 500 steps that we analyzed. Click OK. So you can see there it's created 47 load cases starting at 201, and we can look at those. They'll now appear in the load case list. There they are in green, and you can tell which one each step comes from. So 201 comes from step 14. It's not choosing consecutive steps. You can see there's gaps in the steps there as it chooses the steps that give the worst results, or the minimum and maximum results. So if we look at one of those, turn on the deflections, and I'll just change the scale a bit. You can see that's one load case. That's another one. So these are just snapshots in time at various points through the 40-second duration that we analysed. And you can also get bending moments and shear forces and so forth, as you would normally expect. So we can also get a report of those load cases. So just for a brief report, I'll just look at the reactions, but we can also get displacements, forces, moments, stresses, everything. And I'll just do load cases, say 201 to 205, so just some of those step load cases. So there you can see the results of those. So load case 204 comes from step 17, which happens at 1.28 seconds in transient load case 100. Now if you wanted to combine those step load cases with other non-dynamic load cases such as self-weight or live load or something else like that, you can also do that using the same procedure. So let's say we combine it with self-weight of the structure, so load case 1. In order to do that, we go back to this option, and then down in this table here we can just fill this out to create those extra load combinations. So with that line there, what I've done here is create some combination load cases that start with number 301, and they factor up the step load cases that are starting at 201 by a factor of 1, and they're combining those with load case 1 factored by 1. Maybe I'll change that to 2 just so that it's not all a whole series of 1s everywhere. So now load combinations starting at 301 are combining the step load cases that start at 201 with load case 2 factored by 1. I hope that makes sense. So we've recreated our 47 load cases, plus we've also created those combination load cases. So if we look in the combinations data sheet and just scroll down, you can see here's our combinations now starting with 301. So if I click on that, you can see that's a combination of load case 2 factored by 1 plus step load case 201 factored by 1, and then 302 is 2 plus 202, 303 is 2 plus 303, or 303 is 2 plus 203, etc. And they also appear in the load case drop down, so you can view the displacements and forces and moments and reactions just like you could with any other load case. And you can then use those generated load cases in your steel design or concrete design just as though they'd come from a static analysis. So just to finish off, I'll just show you a section in the help system that you may want to read if you're looking for more information. So if you go to the analysis chapter and look at the step-by-step guide to harmonic analysis, just takes you step by step through all the steps that you have to follow to get to the end result. And there's a similar thing with the transient response analysis.